Now next we studied so far about the boundary layer, the development of boundary layer or a flat plate, and then the various parameters, the thickness of the boundary layer, the shear stress, the friction coefficient, etc. we can calculate, and we discuss the expressions for laminar boundary layer and for turbulent boundary layer. Next important phenomena is boundary layer separation. For boundary layer separation, as you can see here, that on this curved surface, this fluid will flow past this surface of the body, but you can see here that at this point S, clear, the velocity is 0 here. Clear, the velocity is 0 here in the sense that you can see that the velocity gradient, that is 0. Now in this case onward, after this S, you can see that there is a backflow generated, or in other words, the fluid has separated from the surface, because from here the fluid stick to the surface, but at point S the fluid separates, and you can see here that a recirculation will take place, and this is known as boundary layer separation. Now this boundary layer separation is undesirable. Why? Because this boundary layer separation, it increases the drag forces on bodies. So this is undesirable phenomena, and we would like to decrease, clear, the drag force. So that's why we would like to avoid this boundary layer separation. I will explain the mechanics that why boundary layer separates from the surface of the body and what is the effect of this. You can see here that this is a fluid flowing past this object, and you can see that at this point here the boundary layer separates, and you can see that this results into the wake size, you can see, is more, and it will result into more drag force on this object. And the reason is that we have separation here. The boundary layer, it sticks to the surface and then it separates at point. So that point is known as the separation point. And after that, you can see the boundary layer does not stick with the surface of the object, and there is a recirculation, clear, reverse flow that will occur. You can see here. So this is undesirable condition. We have to avoid this. First, we understand that how this condition develops, and then what can be different methods that we can use to avoid this boundary layer separation. Clear? So you can see here in this diagram that because of the boundary layer separation, which is shown here, the average pressure on the rear half of the cylinder is considerably less than that on the front half. Thus, a large pressure drag is developed, even though because of small viscosity, the viscous shear drag may be quite small. So because of this boundary layer separation, what happens is that large pressure drag is developed. And so far we studied that because the drag forces are resistive forces, we would like to minimize them. Clear? So you can see in this here the flow past the object. You can see this is for an ellipse shaped body, and you can see that at this point the boundary layer separates on both sides also. So this can result in increased drag force. Now let us first see the mechanics of this boundary layer separation, that why boundary layer separates, and then we studied how to avoid this condition. Clear? Now in this case you can see that for a curved object as you saw in the previous slide, for curved objects, this boundary layer separation can take place because of difference in pressure gradients that exist from point to point. So before I explain this figure, you can see here the effect of shape on this boundary layer separation. You can see here when we have a kind of flat plate, you see there is no separation. You can see here boundary layer will be developed, clear, but you can see the flow does not separate at any point on this surface. For a flat plate, that's why the assumption is that the pressure gradient, that is zero. So because of that, you can see there is no separation. But as we change the shape, more curve shape, then in that case you will see that the separation will take place. You can see here, now we change the shape, so you can see that flow separation will take place. So in this case, you can see the flow separation has taken place, and there is a reverse flow, clear? And what will be the effect of this? That it will increase the drag force on the body. So this is undesirable situation. But if you can see that if we have a kind of a flat plate, then the flow separation is avoided. So now you know that when we have a curved surface, we can observe this flow separation or boundary layer separation, clear? For a flat plate, the boundary layer will stick to the entire surface till the end. Now, this phenomena, why it occurs? First, we study the mechanics of this, and then how we can avoid this boundary layer separation. You can see here that this fluid, as it moves past this surface, so what is happening is that from point A to point B, we have a pressure gradient dp by dx, and now here the velocity is denoted by u. So essentially we are considering flow in the x direction, clear? So that's why this u is used, which I said, but we still denote this by v. So anyhow, this figure is taken from a book where it is denoted by u, so no need to change it. Just for understanding, it is v or u, so it is the same, clear? We are using v just to stick to the sign convention, but you can use u, etc., and so on. Okay, now in this case, the pressure gradient is less than 0, means dp by dx is less than 0, means change in pressure in x direction is less than 0. What it means? That we are moving, this flow is occurring from high pressure to low pressure. This flow is occurring from high pressure to low pressure, clear? What we can say is that we have high pressure, and in here we have low pressure. Low P. So this is what we call it as favorable gradient. This is favorable gradient for flow to occur because the flow occur from high pressure to low pressure, clear? So that's why in this case you can see that the change du by dy, that is greater than 0. We have the velocity gradient that is positive, clear? So we have a favorable pressure gradient as the flow occurs from here to here. Now when we have at the separation point, what essentially becomes that from this low P, we are now moving towards high P. Again, now we are moving from here towards high P. At here high pressure, this is what you saw here. in this, that the average pressure on the rear half of the cylinder is considerably less than that on the front half. So we are moving from low pressure to high pressure, this zone here. So now in this case, when you are moving from high pressure to low pressure, you see the pressure is in this direction. The pressure is also acting in this direction. That's why the flow occurs. So we have a positive velocity gradient. This is what we observed so far. Now at this point here, when we move from low pressure to high pressure, it means you are moving from low energy to high energy. Just to understand, think like this. So it means that you are pushing something. Clear? So it means that you are pushing against. That's why this pressure, which is favorable pressure gradient, after passing the fluid through this point here, the pressure is high. So it means that the pressure it acts, or let me draw it here. The pressure is essentially in this direction. Means we are acting against the pressure because the fluid is moving from low to high pressure. So the pressure is in this direction. So that's why it is pushing this velocity gradient in this direction. You see, it is pushing the velocity gradient in this direction. That's why you see that the velocity, it is pushed in this direction. That's why you can see the pushing. And at this point C, this velocity gradient becomes 0, from greater than 0 to equal to 0. At this point here, this is at this point here. And if the fluid further moves, then what will happen? The pressure is still pushing it. So that at this point here, a negative velocity gradient is developed. And because of this negative velocity gradient, the reason is that you have a adverse pressure gradient. This is known as adverse pressure gradient because the change in pressure per unit x is greater than 0, means you are moving from low pressure to high pressure. So what will be the result? It means that the pressure is pushing this velocity in backward direction. That's why you see the velocity gradient that has become negative. So because of this, what is happening is that this velocity gradient is negative. So what will be the effect? It means the flow will occur in this direction. The flow is essentially occurring in this direction. So now this flow is coming in this direction. You see, this flow is coming in this direction due to the adverse pressure gradient, and this flow is occurring in this direction from B to C. When these two meet, the flow cannot come here. Can the flow come here? It is solid body. No, cannot come here. That's why the flow will try to move in this direction. Or in other words, let me correctly draw this. What will happen that the fluid will detach and it will move in this direction as shown by this dashed line, separation streamline. Because this fluid is coming here, this fluid is coming here, where the fluid particle will go. Cannot come here, body surface, so it will get separated from this surface. And this is due to this reverse flow here. So this is the mechanics that how the separation of boundary layer takes place. And this is the separation point. Now, this separation and separation point to occur, it will depend on several factors. It is not constant that for every type of flow, the point will be essentially this point. No, this occurrence will depend on several factors, as you saw in the video. Because you can see this is not constant. If I show you again, you can see here the point of separation, it is not constant. You can see here the body, now the shape is curved. separation takes place, and you can see the separation, it moves. See the separation, it moves. So it depends on the different flow conditions. This is the mechanics behind why we have the boundary layer separation. Now, to see the boundary layer separation, Prandtl, he conducted an experiment for boundary layer separation. He placed a cylinder in a moving fluid, and when he increased the velocity in part B, he increased the velocity, you can see that separation has taken place. And on further increasing the velocity, these vortices are moving upward, initially at D here, but now coming towards point A and point B. So this is how experimentally we can observe this boundary layer separation, which I show you in this video also. You can see here the boundary layer separation. So what essentially he did is that he increased the velocity. Here the boundary layer sticks to the surface with low velocity, but when you increase the velocity, then you can see separation has taken place, and on further increasing the velocity, these vortices have become more prominent and shifting upward. Now, as we learn that boundary layer separation is undesirable because it increases the drag force, so now we study how to prevent boundary layer separation. So the separation of boundary layer in a turbulent flow may be prevented in order to have reduced drag. Many methods have been suggested. We will study some of them. If you want to study more methods, you can study the book. For example, it's available in your library also. Fluid Mechanics, Hydraulics and Fluid Mechanics by E.H. Levitt. You can study that book. More than 2 methods I will explain here. More than 2 methods are explained in that book. So different methods are suggested. We will study a couple of them. Number 1 is by providing slots near the leading edge. So you can see here that this is the object, for example, the airfoil. Now you can see here that the boundary layer, it gets separated here. So this here you see, and what will be the effect of this? That it will increase the drag force on the body. Now to avoid this situation, if slots are provided in this body, then you can see that the boundary layer separation can be prevented here. So in this case, the drag force will be less as compared to this case by providing slots near the leading edge. One of the method in order to prevent the boundary layer separation. Example of this, before we discuss the another method, this is what is actually done in case of aeroplane wings also. So we have this wing slate clear here, and we have flaps, slates and flaps that are provided to better operate clear the flying of an aeroplane. So you see here that the air will flow. This will prevent when the aeroplane is climbing. So you see here, this will prevent the boundary layer separation. The drag force will reduce and the lift force will be more clear. You can see here. And when the aeroplane is cruising normal speed flying through the air, so then in that case you can see the lift force because of increasing area here. See, beyond, we are going beyond this object here and here, the lift force can be maintained and it can fly in this fashion. Commonly you have seen that these are called spoilers. These are called spoilers that are raised, and these are called flaps. Clear? These are called flaps. They are moved down. So the idea here is that during landing, this is done to increase the drag force because we want to stop the aeroplane as soon as possible and decrease the lift force, because now from here the air coming and it will go up instead of going down. So it will try to push down the aeroplane. or in this, or you can say that it will try to minimize the lift force. So this is how you might have observed when the aeroplane during landing operation, you might have seen this situation. Clear? So clean configuration, in this case we have the flaps, the spoilers, and the slats here, and we have, this is the spoiler and this is the slats. We will not go into detail aerodynamics. Aeronautical engineering can be more concerned with this, but just to understand how it works, we just quickly and briefly go through it. So this is a situation that you can use for climb, cruise, and descent. Then increase wing area during takeoff and initial climb. Clear? You can see here, during takeoff, this flows here and it will avoid the boundary layer separation, reduce the drag force. So during takeoff, the drag force we want to minimize, and we can climb because you can see the area is more. See? So the lift will be more. If you do not have these things, see, if you cut off this, so the area essentially will reduce for the lift force. So that's why, because of this, it helps to increase the lift force. We just go very briefly to it. And then maximum lift and high drag. Approach to landing. So now approach to landing, still we need the lift, but we want to increase the drag force, slow down. So then in that case, still the lift will be more, but you see that now these are down. So now you can see that for the drag forces, the area has increased. So that's why it will result into high drag. That's why you saw that the aeroplane wings, these flaps that are extended here. And in this case, when the aeroplane is landing, we need maximum drag and reduced lift. So then you can see the spoilers up. So instead of going down, the spoiler up, so the lift will be reduced. And still you can see the flaps, they are extended, we can say, or in this fashion, so the drag force will increase, because we want to reduce the lift during landing and increase the drag so that the aeroplane can stop in as soon as possible. And this is what you commonly see. Whenever the aeroplane is landing, you can see the spoilers are up to reduce the lift force, and these are flaps. They are down to increase the drag force so that it can stop quickly. Clear? Now you can see that when we have a clean, clear, this is on the airfoil. So you can see here that if we do not have these slots provided, etc., flaps, clear. So in this case, what will happen? You can see that the lift coefficient is 1.52. And this is the angle of attack that we discuss. But if you can see here that for double slotted flaps that we commonly you see in the aeroplanes, as you saw in the picture before, the lift coefficient is increased to 3.48, 3.5 we can say, from 1.5 to 3.5 because of this arrangement. But there is a negative side of this arrangement that you can see here. For a clean, no flaps, you can see here the drag coefficient is around, let's say, 0.06. But if we have the double slotted flaps, then in that case you can see here that it has increased a lot, the drag coefficient. So it means that in this case, the aeroplane engine will have to use more power to overcome this increased drag force. So this is how the mechanics of this lift and drag forces an aeroplane wing occurs. But we discuss very brief, since we are not students of aeronautical engineering, but just for basic understanding, this much information is sufficient. Next, the second is rotating cylinder as leading edge. So in this case, you can see that this is B, and in this case, what is happening that when the flow occurs, you can see the boundary layer separation, and this results into increased drag. If we want to reduce the boundary layer separation, we can rotate this cylinder. Rotate the cylinder, you can see that the streamlines, they have deviated, and this wake has been reduced. So it means that it will help reduce the drag force. Clear? But then this rotation of a cylinder in a moving fluid, this lead to another phenomena. This lead to another phenomena which is known as the Magnus effect. On one side, it can help to reduce the drag force by rotation of this body in a moving fluid, clear? But then this rotation gives us another important phenomena which is known as the Magnus effect. So what is the Magnus effect? Just like we discussed the lift force concept, when we have the object which is rotating in the fluid, so you see here on this side, you see here the streamlines very close to each other, means that the velocity is more. So consequently, the pressure will be decreasing. And in here, you see the rotation of this body, it is opposite to the moving fluid. So what will happen that it will try to slow down here. That's why you can see the streamlines are further apart and the velocity decrease. So pressure will increase. So again, more pressure here, less pressure here. A lift force will be created in the upward direction for this setup. And this is known as the Magnus effect. Clear? So this Magnus effect, generation of a sidewise force on a spinning cylindrical or spherical solid immersed in a fluid when there is relative motion between the spinning body and the fluid. It means that if a body is rotating in a moving fluid, a force will be generated on there that is known as Magnus effect. And this Magnus effect explains the curved path that is followed by a tennis ball or driven golf ball and the trajectory or spinning of artillery shell. When we hit a ball, the ball moves in a curved path. That explains, that is the Magnus effect. Because the ball is rotating in a moving fluid and it moves in the fluid. So because of that, the curved path that is traced by the moving object, that is known as the Magnus effect. So this Magnus effect that is responsible for the curved path of these moving balls, etc. Now the phenomena of producing lift by the rotation of a solid body is called the Magnus effect. As you already saw that when this body is for ideal fluid, that's why this is for ideal fluid, idealized. So that's why there is no separation of the boundary layer, or you can say the disturbed region which you saw here, this one, because this is for ideal fluid. So in this case, you can see the streamlines, they move like this. But if the body is rotated, you can see the behavior of the streamlines. High velocity, low pressure. In here, low velocity, high pressure, as I already discussed, and that this will result into a lift in this direction. Remember, if for example, this is here and this is here, then the force direction will be downward. So this is not that always the force is acting upward. This depends on the body, clear? So remember that it is just for these given cases that the forces are acting upward. Similarly, you might have observed that when we hit a football, soccer ball, so you can see that because of it is rotating and the fluid flowing past this object, so that's why now in this case you can see due to the Magnus force is acting down. Depends on the condition. So this effect is known as Magnus effect, and this explains why the balls, etc., when they move through the air, why they follow a curved path. Clear? You can see here, if you have watched the soccer balls, etc., you might have seen that when you hit the ball, it moves in a curved path. Clear? So this is due to the Magnus effect. The more you are able to master this Magnus effect, you can hit the ball to the goal post. This will depend how you generate this Magnus force. This will be the expertise of this footballer. Clear? You can see here, this moves. This is due to the Magnus effect. If you can master this, so this is the technique which is used by the, for example, Roberto Carlos, to put the ball into the goal post. Clear? So this is very interesting phenomenon. Now, coming to another interesting thing is that Flatner, who was a German and then he worked in the US Navy, he developed a rotor based on this concept, which is what is known as Flatner rotor. Clear? He said that if in a ship we have this kind of rotors, it will try to push, because a force is generated, as we saw here, a force is generated, Magnus force. He come up with the idea that if we have this type of rotors that are installed in a ship, and if the air is flowing across here, then a force will be generated and it can push this boat in the forward direction, and it can be an economical situation as compared to we are using the engines to push this large vessel or boat, etc., or ship in the forward direction. Clear? So he come up with this idea, and this was known as Flatner rotor. Clear? And then what happens is that it was used in the ships. You can see here Magnus effect in shipbuilding. So rotor ships were used. This was done in the 1920s, I think. And you can see mast-like cylinders for propulsion to push this large vessel which is floating on water in the forward direction. The effect is used as a special type of ship stabilizer consisting of a rotating cylinder mounted beneath the water line and emerging laterally. So because the wind is important, if this Magnus effect has to work. If there is no wind, it will not work. So that's why wind was still required, so that the Magnus effect, it can push large ships in the forward direction and we can save fuel. It can be economical. Clear? But later on it was found that although some transatlantic sails were made with these type of ships, clear, boats, etc., but then it was found to be uneconomical. So that's why this idea was no longer followed. You can see here, you can have an experiment of this. Now we have two rotors, and if you make an arrangement to flow the air across, now the rotors are rotating, and now he is holding a fan. You can see the boat is moving in the forward direction. This is due to Magnus effect. So you can see that very interesting phenomena. Because of that, these ships were built, but later on it was found that these are uneconomical. Now we come to discuss reducing the drag forces on bodies. So you can see here that in this case, when a smooth sphere it is moving through the fluid, the drag coefficient is 0.4. But in this case, the nose or the front of this sphere is made rough. Clear? This is made rough, artificially made rough. So then in that case, this drag coefficient is reduced to 0.2 from 0.4. Now in this case, you can see we rough the surface. So the added roughness and boundary layer, turbulent boundary layer, cause an increase in friction drag. Because from rough surface to smooth surface to rough surface, clear? You artificially rough. But this becomes secondary importance, because you can see that the wake that is pushed back as compared to here. You see, the wake is here from here onward. But due to making the surface rough, the front artificially here with this, you can see that of course it will increase the friction drag because you rough the surface and make the boundary layer more turbulent. But you can see that this becomes secondary. You can see that the main important thing is this turbulent wake is pushed back. And when this turbulent wake is pushed back, you can see that the drag coefficient is reduced from 0.4 to 0.2. So it means this will move faster as compared to this. And this is the reason why the golf ball is made rough. You can see the golf ball, it is dimpled. It is not smooth. Because that dimpled golf ball, it will travel faster as compared to a smooth ball. This is the reason why the golf ball is made rough, the surface. You can see here again, in this case, we have added a trip here that is added. So the addition of a tripwire to induce transition to turbulent changes the separation line further. You can see here, this is separation here. But now in this case, the turbulent separation is here. So reducing the size of the wake and thus drastically reducing the overall drag. You can see here that when we have a smooth sphere, a smooth ball, you can see the separation is here. So this will result into increased drag. You can see thick wake. But by making the surface rough, you see the golf ball, the surface is made rough. You can see the thick wake that is made thin. So what will happen? That's why the golf ball, it will travel more distance as compared to smooth ball. So this is the main reason why surface of the golf ball is dimpled. You can see depressions are provided on it. A smooth surface ball would have greater overall drag and would travel only about 60% as far when driven. So you can see here that turbulent boundary layer, the golf ball, you can see here, it will travel faster as compared to the laminar boundary layer. So it means this ball will move faster, the upper one, smaller one, as compared to this ball here. So this is the reason why you have seen that the golf ball, it is dimpled, because it will, when you hit the golf ball, it will travel more distance as compared to a ball which is smooth surface. Similarly, you can see in this diagram streamlining that we earlier discussed. You can see here that this is the top plane view for a motor vehicle delivery van. So just by making these edges round, you can see that the point of separation has been taken back. Clear? So that's why you see that the drag coefficient here is significantly reduced as compared to the drag coefficient here. It means that this vehicle will be traveling faster as compared to this shape vehicle. Clear? So this is how we do streamlining of bodies, that I already explained in the previous class, that we are trying to streamline the bodies so as to, the objective is to reduce the drag coefficient and to reduce the drag force so that it can travel faster and coverage per gallon is more economical. Now we discuss a few problems to wind up this chapter. Although much can be discussed in this chapter, but from the subject point of view, this much discussion is sufficient. Now we have, this problem is from the textbook. Find the shear stress and the thickness of the boundary layer. Part A of the question is at the center and B at the trailing edge of smooth flat plate that is 10 feet wide and 2 feet parallel to the flow immersed in 60° Fahrenheit water flowing at an undisturbed velocity of 3 foot per second. Assume a laminar boundary layer over the whole plate. Also find the total friction drag on one side of the plate. Clear? So the solution includes that for this temperature of water, you will read the properties for 60° F, clear, table A1, the density, kinematic viscosity, and the dynamic viscosity values you can read from the table appendix in the book. And at the center of the plate, because the plate is how much? 2 feet parallel to the flow. So the total length of the plate is 2 feet. Now at the center, it is said that at the center, you calculate the shear stress and the thickness of boundary layer. So we have to calculate the shear stress and thickness of boundary layer at the center, means at x is equal to 1 feet. So at x is equal to 1 foot, you want to calculate the shear stress and thickness of boundary layer. So this shear stress that we earlier discussed is your tau naught, and this is your delta. So for that we need to calculate the Reynolds number, because earlier we stated that we have separate equations for shear stress and thickness of boundary layer and to calculate the friction drag for laminar and turbulent flow. So that's why we need to first determine that is the flow laminar or not. Now it is 247,000. So it means this assumption is okay. Clear? Because what is the critical value? 500,000. So it is less than 500,000. So that's why we have laminar boundary layer. Now you can use that expression. Clear? So for laminar boundary layer, the thickness of boundary layer is given by this equation. You will calculate Rx, which is already calculated at x is equal to 1, and at x is equal to 1, the thickness of the boundary layer, it is given by this value. Similarly, next is to calculate the shear stress. So the shear stress for laminar boundary layer is given by this expression at a distance x. Rx and x, at a distance x, the shear stress. So this is calculated as 0.01167 pounds per square feet. Now next we have to calculate the same for at the trailing edge of smooth plate. So trailing edge means end, means at 2 feet. So at the trailing edge, x is equal to 2 feet and Rx will be equal to this much, still less than 500,000. So it means that the entire boundary layer for the whole plate is laminar. So again, you use these equations to calculate the thickness of the boundary layer and the shear stress at the trailing edge. Clear? So you can see here that the shear stress is inversely proportional to x. When the x is increased, shear stress has reduced. You can see here 0.008 and in here 0.011. Now drag on one side of the plate. This is part C of the question. Find the total friction drag on one side of the plate. So CF for laminar condition, we can calculate for this. Now it is R, not Rx. See, this is R, not Rx. It means that this is for the average value for the entire plate length. Because we discuss if at any distance x you want to calculate CF, you remember it was denoted by CF comma x. It is not that one. So that is at any distance x, then you will use Rx. When you see CF and only R, it means it is for the entire length of the body. So remember this when you solve the problems. So now we calculate CF for the entire length. It is 2 feet and this is R. So Rx is equal to R because it is for the entire length. It is this much CF. And now this is the equation that we studied. In that case, this is area A. This is the characteristic area A. So we have flat plate, width into length. So this CF, this is now the average value for the entire length. So we calculate the drag force on one side of the plate, put in this equation, everything is known. It is 0.330 pound. So this is the drag force on one side of the plate. Remember this equation that we discussed. So this FF, which is acting on one side, that is given by this equation. It will also be on both sides. You see, FF will be here also. But commonly we just calculate on one side and the same value applies due to symmetry on the bottom. So that's why this equation that we commonly use, it is on one side of the plate. That's why in the question it is written. We consider another problem from the textbook. An 85-meter long streamlined train has 2.5-meter high sides and a 2-meter wide top. Compute the power required to overcome the skin friction drag when the train is traveling at 40 meters per second through the standard atmosphere at sea level, assuming the drag on the sides and top to be equal to that on one side of a flat plate 7.5 meter wide and 85 meter long. So now in order to calculate the drag force acting on a train, they say you consider the train to be equivalent to a flat plate. The drag force on one side of a flat plate that is 7.5 meter wide and 85 meter long, that drag force will be same as acting on 85 meter long streamlined train. Just you calculate the drag force here for a flat plate, that will be same as for a train. Clear? So now for sea level, it is given that at sea level you can calculate the properties of the fluid from table A3 for air, and then R is equal to LV by nu, the Reynolds number, or R is equal to 2.33 into 10 power 8. Now it is greater than 500,000, so we have turbulent flow. You can see here this is greater than 500,000. So we have turbulent, and then in turbulent flow boundary layer there are two equations. So greater than 10.7, we studied that this is the equation to calculate the friction coefficient for R greater than 10 power 7. So you can calculate CF which is given by this equation. And then for a flat plate, you calculate the friction drag force. Now these are the dimensions for a flat plate, the area. Clear? So this is 1184 Newton. And because it is stated in the problem that on one side of the flat plate the force is acting, it is equivalent to acting on this streamlined train. Now power, as you know, that power is equal to force into velocity. So just we multiply this force with the velocity of the train, because the train is traveling with a velocity of 40 meters per second. So this is the power that is required to overcome the skin friction drag. Now we consider another problem. So a 20 millimeter diameter harpoon. Harpoon is in the shape of a missile, just a tip that we have. It is of this shape here, that is moving through clear with a sharp tip, that is launched at 6 meters per second at 15 degrees Celsius in water. Find the friction drag on this harpoon and the maximum thickness of the boundary layer. So now in this case, from table A1 for water at 15 degrees C, you can read these values. And now at x is equal to c, just to see that if a transition occurs or not. Clear? So we calculate the critical distance xc. So this distance is 0.0949. It is less than L. What is the length? That is 1.8 meter long. So it means that a transition regime exists. This is less than L. A transition region must exist. So R will be equal to this much, clear? And then for transition regime, the CF is given by this expression, clear? And CF you calculate, it turns out to be this much. But remember, if you calculate this CF for a boundary layer, in that case, it was not written. This is for a boundary layer, turbulent. So you will still get the result very close to this one. So that's why in such type of problems you consider to calculate CF for transition region or make it for turbulent condition. You will get approximately very close same answer. But anyhow, if we want to be accurate, then we can say that use this equation to calculate CF. Clear? So now to calculate the friction drag force, we always use this equation. And now in this case, you calculate the area. This is not a flat plate, but it has a diameter and a length. So that's why pi d into L, that is the characteristic area. And it is given the friction force, that is equal to 5.8 Newton. The maximum thickness of the boundary layer. So in this case, we use the thickness for the turbulent boundary layer. And then in that case, the maximum thickness, what will be x for maximum thickness? As you saw that as the distance increases, the thickness increases. So that's why this x will be 1.8 meter. Clear? Because the boundary layer thickness we saw earlier in the diagram, that as x increases, the thickness increases. So that's why this thickness will be at the trailing edge. X is equal to 1.8. Less than that, you see delta will be less than that. But it is asked maximum thickness. So for that, x should be maximum, means the entire length. So this is the thickness of the maximum thickness of the boundary layer.